Let's imagine we want to look at the motion of the Earth, and the Earth is going around the sun. So here's the Earth, and it's going around the sun in some somewhat elliptical orbit. But the sun is also going around the galaxy. So the galaxy is rotating, and then the galaxy is moving around other galaxies. The motion of the Earth is very, very complicated. But what we can do is let's move into the center of mass frame of reference of the Earth and the sun, and just look at the motion of the Earth around the sun, and not worry about the motion of the sun through the galaxy and the motion of the galaxy through the rest of the universe and things like that. How can we go about doing that? What we do is, as I said, we move into the frame of reference of the center of mass. It's called the center of mass frame of reference, or the center of mass frame. Now, how can we go about doing that mathematically? What does that do with these equations we've been looking at? That's what we're going to look at next. What we want to do is to try and figure out how different perspectives would measure different velocities. Or if something is moving, how one frame of reference might measure the velocity versus how another frame of reference would measure that velocity. That sounds a little complicated, but let's take a look at what this means. Let's imagine that we've got a coordinate system, let's say over here, and I'm going to call this the A coordinate system. And then we've got maybe another coordinate system over here. I'll call this the B coordinate system. So this might be, say, the coordinate system of us watching the Earth go around the sun, and the sun go around the galaxy, and the galaxy going through space, or something like that. This might be a very complicated position. While this one might be traveling along with the Earth and the sun, so this might be in the center of mass frame, or something like that, to make it a little easier. Something like that. And then we've got some object over here. We'll call this object C. And C is the object that we're trying to observe. Maybe this is the Earth and the sun or something. Let's imagine that we measure the position of this object from this frame of reference. So we'll call this position vector here. So this is our position vector R. Now I'm going to write this as R, the position of object C. So R sub C, that's the position of object C, but it's measured by object A. So I'm going to call this RCA. So it's the position of object C, the first subscript, measured by object A, the second subscript. While, let's say, reference frame B measures the position of that thing, and we'll call that R what? So that's going to be the position of object C, again, but now measured by object B, or reference frame B. Okay, good. Now, we need to have a position of these two things relative to each other. So let's put in one more vector here. We'll call this vector, and you could do it one way or the other. I'll just say from this direction. We'll call this the position of object B measured by object A. All right, great. Now, what are the relationships between these things? Well, what we see is that this vector is the sum of these two vectors. We see that RCA is equal to RBA plus RCB. But I'm going to reverse those. I'm going to put that as RCB plus RBA. Okay, we see that this vector is then this vector plus this vector, or this vector plus that vector. And that's actually the way I wrote it. Now let's differentiate this result. Differentiate both sides with respect to t. What do we have? d by dt of this side equals d by dt of this plus d by dt of this, which gives us what? What's our result here? Well, the derivative of the position with respect to time is the velocity. So VCA is equal to VCB plus VBA. VBA. There we go. All right, this is a very, very important result. Whoops. The velocity of this object measured by reference A, or coordinate system A, you might say, is equal to the velocity of this object measured by reference B, but plus the velocity of B measured by A. We could put this over on the other side and switch the indices around if we want, but this makes it one way of remembering how these go. Notice that we've got CB and then BA. CB, BA. Kind of the B's are in the middle, and what do we end up with? We have C and A on the outside, and that kind of matches up the order that we have the C and A over here. So that's one way to kind of help us remember. We've got VCA, we have C and A, and then we can put another index in between them, CB, BA. And that kind of helps us remember what the order of these vectors is. Very, very good. What we want to do is use this result in terms of the center of mass. But let's just take a quick look at an example of how this actually works. That might help us a little bit. Let's imagine that we have a river here and the water is flowing to the right. So the velocity of the river is to the right at, let's say, 3 meters per second. In that direction. And then a boat comes along, and there someone puts a boat in the water. And that boat, they are going to try and start rowing that boat across the water relative to the water. So the water is dragging the boat along, but they're moving the boat relative to the water, let's say in that direction, at 4 meters per second. Okay? Now, we've got a motion of the river that's relative to the ground, you might say. We have a motion of the boat that's relative to the river. What is the boat going to do relative to the ground? In other words, thinking about this, what is the velocity of the boat relative to the ground? So the velocity of BG, the velocity of the boat relative to the ground. Well, what do we know? How can we deal with something like that? Well, from what we've seen before, we can say that this must be equal to the sum of two velocities. This would be the velocity of the boat relative to the river. And then the velocity of the river relative to the ground. Okay, well there we go. Well, what we have to do is just add these two vectors. What is the velocity of the boat relative to the river? Well, it is a vector that looks like this. It's up this way with a magnitude of 4 meters per second. What is the velocity of the river relative to the ground? Well, it is going to the right at 3 meters per second. We have to add it onto this vector. It looks like that, 3 meters per second. So what is the result? What is the velocity of the boat relative to the ground? Well, all we have to do is add these two vectors together. What do we get? We get a vector that looks like that. And we could figure out what's the magnitude of that vector. Well, these two happen to be perpendicular, just for this example. We have one this way and one that way. So 3, 4, well, we know this is a 3, 4, 5 triangle. This is going to be 5 meters per second. And then we could figure out what's that angle, the inverse tangent of 3 over 4. We could figure out what that angle was if we wanted. But the important point is that when we want to measure the velocity of something relative to something else, in other words, if two different observers are going to be trying to measure something like the velocity or the position of something, we have a very simple relationship between the velocities of those objects. The velocity of, in general, we could say the velocity of AB is equal to the velocity of AC plus CB, or in this case, BG on the outside, and then R on the inside, BR plus RG. Okay, great. Let's take a look at how this applies to the center of mass of a system. Let's imagine we have some system of a whole bunch of masses, M1, M2, M3, and we're going to measure the positions and velocities of these things. Let's imagine that we've got some coordinate system, some general coordinate system over here, and we measure these positions and they have positions R1, R2, R3. And then this system has a center of mass. We calculate whatever the center of mass is, and we end up with a position of the center of mass. We'll call that RCM. What I want to do now is, rather than measure the positions of the objects from this coordinate system over here, I want to measure the positions relative to the center of mass. So I'm going to measure these positions here, measured from the center of mass. So I'm going to call these R prime. So this would be R1 prime, and then the position of this one would be R2 prime, R3 prime, like that. So what do we have? We know that R1 prime plus RCM, we usually might think of this as RCM plus R1 prime. I'm just going to reverse that order. R1 prime plus RCM is equal to R1. And now let's differentiate these. And what do we get? And then likewise, R2 prime plus RCM will be R2, R3 prime plus RCM equals R3. So let's differentiate these. What do we get? d by dt, d by dt, d by dt. Okay? So what do we get? Well, this I'm going to call V1. So that's the velocity of our first particle measured by our general coordinate system. This one, I'm going to call this U1. So this is the velocity measured by the center of mass, so to speak. In other words, measured in the center of mass frame. And then what is this? This is the velocity of the center of mass, plus VCM. So what is U1? U1 is equal to V1 minus the velocity of the center of mass. So it's the original measured velocity minus the velocity of the center of mass. Okay, great. We're going to start from there. Okay, great. Okay, great. Let's add up the mass times all of these velocities. In other words, what's the total momentum of the particles measured in the center of mass frame? What I want to do is I want to calculate m1u1 plus m2u2 plus m3u3. So what is this? This is m1 times the velocity of particle 1 as measured in the center of mass frame, plus m2u2, which would be the momentum of particle 2 measured in the center of mass frame, plus et cetera, et cetera. So this is basically the momentum of the system measured in the center of mass frame. So what is this? This is the total momentum measured in center of the mass frame. Okay? Let's see what that is. Well, what do we get? M1U1, that will be M1V1 minus M1VCM. And then M2U2, that will be plus M2V2 minus M2VCM. And then M3U3, so that will be plus M3V3 minus M3VCM, okay, plus et cetera, et cetera. Now, what are all of these? This will be M1V1 plus M2V2 plus M3V3 plus et cetera, et cetera. And then this is minus, well, all of these are VCM, so this is M1 plus M2 plus M3, et cetera, times VCM. But what is this? M1V1 plus M2V2 plus M3V3. That is the sum of each individual momentum for each particle added all together, but we already saw that that was equal to the total mass times the velocity, whoops, I did it like this, times the velocity of the center of mass. We already calculated that. Minus What's m1 plus m2 plus m3? Well, that's the total mass times the velocity of the center of mass. Oh, but that is exactly the same, and that is 0. So what do we have? The left side is equal to 0. That is an amazing result. That when we look at the total momentum in the center of mass frame, the momentum of the system, the internal momentum, the sum of all of the internal momenta of the system is 0. In other words, the net momentum in the system relative to the center of mass, is 0. That is a very, very interesting result.